All right, so this is part 2 of our rational functions notes. So today, in this part of the video, we're going to talk about graphing rational functions. At the top of the screen here, you can see the 5 key steps as we graph these rational functions. We're going to find our intercepts, our y-intercept and our x-intercept. And then we're also going to find our asymptotes, vertical and horizontal. And then beyond finding our intercepts and asymptotes, we always want to include one extra point on either side of an asymptote, just to get a general sense of the shape of this particular function. So here we have f of x equals 1 over the quantity x minus 1 squared plus 3. So we're going to start by finding our y-intercept. That will be f of 0. And in this case, that will be 1 over negative 1 squared plus 3. Well, that's 1 over negative 1 squared is 1. 1 plus 3 is 4. So our y-intercept occurs at 0, 4. Our x-intercepts occur when our entire function equals 0. So if I were to say 0 equals 1 over x minus 1 quantity squared plus 3, I can subtract 3 from both sides and then multiply times x minus 1 quantity squared to clear my fraction. And what I'll end up with here is a quadratic that I'm going to attempt to solve. Negative 3 will get multiplied times x squared minus 2x plus 1. I can distribute negative 3x squared plus 6x minus 3 minus 1 equals 0. And then I get negative 3x squared plus 6x minus 4. Now, before I go much further, before I try to factor and solve this, I'm going to use the discriminant to see what type of solutions this quadratic would have. Remember the discriminant, b squared minus 4ac. In this case, I would get 36 minus 4 times 4 times 3. I have 2 negatives in there. So that's why I didn't include them. They would offset one another. I would end up with negative 12. All of this to say is I have no real solutions to the quadratic when I was trying to find my x-intercepts. In other words, we won't have any x-intercepts for this particular graph. My vertical asymptotes come from values that give my denominator that would make my denominator 0, so that would be x equals 1. My horizontal asymptote would be at 0. However, this 3 shifts my whole graph up 3, so my horizontal asymptote is at y equals 3. So I'm going to sketch those key pieces of information into my graph here. So I'm going to set up an axis and sketch in some asymptotes. Now, when I sketch in asymptotes, I like these dotted lines. They tell me that they're not really part of the graph. So at x equals 1, and then at y equals 3, these asymptotes will give our graph a little bit of shape. We'll be able to figure out what's going on here. We know that the point 0, 4 is part of our graph. And I want to plot one point on the right side of my vertical asymptote as well. Let's say f of 2. So let's find the point when x equals 2. So in this case, that would be 1 over 1 plus 3. So the point 2, 4 is also on my graph. I have no x-intercepts, so no values will exist beneath my horizontal asymptote, as I can see here. And my graph, I'm going to just follow along that horizontal asymptote and then go up and do the same thing on the other side. And this will flatten out and go off to infinity. As you can see, these graphs look a little bit tricky as compared to some other graphs that we've seen. They're less predictable, I would say, based on the function themselves. So make sure you're being smart about going through these same steps every time. Find your asymptotes, find your intercepts, plot some extra points, and sketch the graph as best you can. Let's look at another graph here. Here we have g of x equals 3x over 3. I'm sorry, 3x minus 3 over x minus 2. And I am in the habit of factoring whenever I can on these functions. Just to make life a little bit easier. My recommendation, if you want to test yourself, is to pause the video and try to find your x-intercepts, your y-intercepts, and both vertical and horizontal asymptotes if they exist. I'm going to pause right now and work through this graph here, and then we'll talk about it in just a moment. All right, everybody, let's see how we did. So like I said last time, we want to be systematic about graphing these. We don't necessarily know exactly what they're going to look like until we go through this process. So I found my y-intercept by plugging in 0 for x. I found my x-intercept by really solving for zeros in my numerator, right? Values that would make the numerator equal 0. I found that to happen when x equals 1. Again, factoring helps. Notice here, really easy to find that x-intercept. My vertical asymptote comes from the numerator, the value that would make the denominator 0. And then my horizontal asymptote comes from the fact that my numerator and denominator have the same degree. So I divide 3 by 1 to get my horizontal asymptote. I included a couple extra points just to ensure that my graph is properly sketched. I included f of 3 and f of 4. I had 2 points to the left of the vertical asymptote already with my x and y intercepts, so I included 2 to the right-hand side of my vertical asymptote. Let's do the same thing here on number 3. Again, I'm going to pause the video. I encourage you to do the same. I'm going to graph all the key, I'm going to find all the key features and graph this function, and then we can reconvene and see how we got there. All right, so here's my work for example 3. What you'll notice on this one, the x and y intercept are the same point. They both occur at the origin. We have vertical asymptotes at positive and negative 2. Again, just as a reminder, factoring that denominator is a good plan, a good move to make if we're ever unsure. It makes it very clear to see that I have 2 vertical asymptotes. For a horizontal asymptote here, the degree is the same in numerator and denominator, so we divide their coefficients, which is where we get our 3. Now, when we have 2 asymptotes like this and not a lot of points to plot, this is where we may want to plot more than just 1 or 2 points. So I decided to plot 1 point to the left of my vertical asymptote and the negative side of the graph, really a point on either side of both of my vertical asymptotes. I'm just evaluating, trying to figure out where exactly this graph goes. As you can see, this is kind of a strange looking graph, one that is a little bit counterintuitive. So certainly one where we want to be systematic in how we approach, finding those key features, plotting specific points to get our sketch just right. The last thing we want to account for here is something called a slant asymptote. So this is a special type of asymptote, and it's more like a horizontal asymptote than a vertical one. If we think about horizontal asymptotes as the end behavior of these rational functions, the slant asymptote behaves similarly. It's going to occur in a very specific circumstance. It's going to occur when the degree of the numerator is 1 more than the degree of the denominator. Now, we can actually find this slant asymptote by dividing, right? If we're able to, we can use synthetic division. If we're not able to, we may have to use long division. We disregard the remainder, and the equation of the quotient is the slant asymptote. So back on page 1, we said that when the degree of the numerator is greater than the degree of the denominator, there is not a horizontal asymptote. In this particular case, because the degree is just 1 more, we will have a slant asymptote. So I want to figure out where that slant asymptote occurs. I'm going to use synthetic division. I'm going to plug 3 in. 1, -4, and -5 are my coefficients. The 1 comes down, I multiply, I add, I multiply, and it doesn't really matter what the remainder is. What we really care about is that our slant asymptote will have the equation x minus 1. Well, from there, we're going to find all our same key features. So we're going to identify our y-intercept. We're going to plug in 0 here for x, and I'll get 5/3 as the y-coordinate. My x-intercepts will come from when my numerator equals 0. We could factor this numerator. We could say that this is x minus 5 times x plus 1. So my x-intercepts would occur at 5, 0, and at -1, 0. We have a vertical asymptote at x equals 3, and we have a slant asymptote at x minus 1. So let's at least set up the structure here before we try to plug in and figure out what else is going on with our graph. So I'm going to start by plotting my vertical asymptote at +3. So let's see, 1, 2, 3. Again, using dotted lines just because that tells us that it's not really part of the function itself. Now I'm going to go ahead and graph our slant asymptote. It has a y-intercept of -1 and a slope of 1. So it would look like this. So that slant asymptote is going to give our function shape. What shape will we have? Well, we're going to have to plot some points. So I have the y-intercept at 0 and just under 2. That occurs right about there. I have x-intercepts at +5. 1, 2, 3, 4, 5. And at -1. And in this case, I'm going to find some other values. I'm going to evaluate when x equals 1. And I would get 4 there. I'm going to evaluate when x equals -2, and I would get -7/5. And then just to make sure we have the general shape, I'm going to evaluate 2 more points when x is 4 and when x is 6. I'll get -5. Sorry, that should be -4. And when x is 6, y is 7/3. So when we plot all these points, we'll start to get a better sense of the shape of this graph. F of 1, 2, 3, 4 is there. It's at -5. Oh, sorry, that is +4. And then f of 6 happens at 2 1/3, right there. So over here, we have part of a graph that looks like this, and it will kind of follow that slant asymptote as it goes further and further. Over on the left-hand side, our graph will bend to the shape of this slant asymptote, and then we'll follow the vertical asymptote as it approaches from the left. So let me just fix one thing. This was at +4, and we were at -5. So that wraps up our notes on rational functions. The big idea here with graphs, we want to be systematic in our approach because these graphs are not very intuitive. You want to make sure you're finding your intercepts, your asymptotes, and you can always plug in an extra couple points to make sure that you have the sketch right. Nice work, everybody.